So we're going to start today by talking about some things that you should already be familiar with from our electron configuration review video and your first year chem class. Orbitals have a particular order that they fill in, and fundamentally, the principle is that nature is lazy. Nature will go for the lowest energy possible state. And that means we fill orbitals from the lowest energy and we don't start higher energy orbitals until the orbitals are full. So that's why we always start with the 1s orbital and fill it, 1s2, then we go up to the 2 subshell. That's the alpha principle. Now, one thing we know is that every electron orbital can have 2 electrons with opposite spin. One is considered spin up, one is considered spin down. That is the Pauli exclusion principle. That's the principle that tells us only 2 electrons in each orbital. So 1s, 2, not 3 or 4. Now, what I know is that adding electrons is actually going to change the energy of the orbital. And if I think about why that is, well, remember, all electrons are negatively charged. And that means all electrons are going to repel each other. And when they're repelling each other, then it takes energy to keep them in that same orbital space. So half-filled orbitals have a lower energy. And that means that falls under Hund's rule, or what I like to call the school bus rule, because it's just like kids getting on the school bus. When a bunch of kids get on the school bus, they'll generally each one takes their own seat. And we don't start filling up the paired seats until the last person gets on the bus and there's no more empty seats. So just like students prefer their own seat, electrons are going to prefer their own orbital because then there won't be that electron-electron repulsion. It makes them more stable, lower energy. And that means that there are a couple of places where that actually changes the electron configuration for some elements. It changes the way the electrons fill. So to think about that, let's think about writing some other electron configurations first. So first things first, let's write the electron configuration for titanium. That's element number 22 with 22 electrons. And I'll have you pause the video and try writing the configuration and then come and check it. So titanium is going to start with, titanium, of course, we'll start with the 1s. We'll fill that with its 2 electrons. So we'll have 1s2, then we'll go to 2s and fill, 2s2, then we'll fill the 2p's, 2p6. Then we'll go to element number 11 and 12. So that's in the s block, 3s2, 3p6. That's at argon. Then after argon, we have to remember that thing where I don't get to make the rules. And so we look at where element number 19 and 20 are, and they're in the S block. So that's what reminds us that we're filling the 4s, and then we fill the 3 Ds. So before S2, that's full, and then titanium would be 2 elements into the D block, so 3D2. So I hope you can see that not a whole lot would change with vanadium. In fact, a lot of the first part of it would remain exactly the same, which is the whole point of having that noble gas shortcut. If I use the noble gas shortcut, then all the way up to 3p6, I would write just as argon. That's what those 18 electrons always look like. And then I would just write 4s2, and now with vanadium, I would have 3d3, because that one extra electron would go into the d orbitals. So we would expect for chromium to have essentially the same configuration. There's my argon shortcut, 4s2, 3d4. But that's not actually what happens. This is not actually the correct configuration for chromium. And the reason that it is because we can find a slightly lower energy state. What happens with chromium is that chromium is going to steal one of these 4s electrons and promote it to the 3D. The reason it does that is because we get half-filled orbitals. So the metaphor I like to use is it's like when your responsible adult comes in and says, oh my gosh, clean your room. Well, you have kind of a couple of options. And what you should do is clean your room. But a lot of times what kids do is they shove everything in the closet and they shut the door. Well, the room isn't really clean, but it looks cleaner. In this case, we're getting half-filled orbitals. It's not as low energy as a full set of orbitals, but it's lower energy than the original configuration. This would give me a full set of half. All 5 of the d orbitals would have one half-filled, would have one electron in, they'd be half-filled, and the 4s would also be half-filled. This is very slightly lower in total energy, and so this is actually the observed electron configuration for chromium. And it's also, if I go down to molybdenum, the same configuration I see there. It's actually not the same configuration for tungsten, because by the time I get down to tungsten, I'm actually also throwing in f orbitals, and there's just a lot more going on, so it doesn't do exactly the same thing. Really, the same principle is going to apply to copper, because what I would expect if I look at where copper is on the periodic table, well, copper I would expect to be 4s2 3d9. Well, if I think about it, if I can steal one electron from that 4s, then I would end up with 4s1 3d10. And so now I have a half-filled orbital, which is in lower energy state, plus I have a full set of d orbitals, which means that's an even better lower energy state. And fundamentally, nature is lazy. If there is a way that nature can arrange so that it is lower energy, that will be the way that we usually see it. Silver does exactly the same thing, which explains part of why silver is one of those weird periodic transition metals on the periodic table. Silver always does +1. And if you look at this configuration, silver is 5s1 4d10. So you can see that lonely s electron there would be very easy to remove. So these are a couple of exceptions. It's not something that would be explicitly tested in and of itself on the AP exam, but it is kind of general chemistry knowledge that might be expected that you would have seen that in a college general chemistry class. So I wanted to make sure I bring it up, because if you don't have to take freshman chem, you'll need to know. So the other thing I wanted to look at was making some anions and cations, especially cations of the transition metals. Because we really should remember how we form ions for the representative elements, the S block and the P block. And that's that we're going to take away or receive electrons so that we make ions that are isoelectronic. They have the same electrons as a noble gas. And that's because that noble gas configuration is completely filled valence electrons, and so it is very, very low energy. So if I take something like magnesium in group 2, if I take those 2 electrons away and I have 10 electrons left, I now have the very low energy configuration of inert neon gas. And so we stay in that low energy state. That's the same reason that sulfur, element 16, will gain 2 electrons. It'll make a sulfur 2- ion. If it makes a sulfur 2- ion, it's filled in the empty slots in its p orbitals. It's now s2p6. It has 18 electrons in the same low energy configuration of an inert gas, argon. We know that from last year. But last year we kind of said, well, there's transition metals, and that's a thing, we'll talk about it next year. Well, it's next year. So let's think a little bit about transition metals. Transition metal ions can form multiple charges because of those multiple electrons in the d orbitals. There's actually something really fundamentally important about forming a transition metal ion. And that is that you need to remember that chemistry is all about valence electrons. And so for a transition metal, we always have to remove the valence electrons before we start removing those d shell electrons. So for example, if I look at titanium or vanadium, the ones that we just wrote an electron configuration for, remember the valence shell is the farthest out shell. 4 is farther out than 3. So the 4 shell is my valence shell, and I'll remove 4s electrons before I start removing any 3d electrons. And that will hold for all of the transition metals. If I am making a ion out of something like ruthenium or palladium, I remove the s electrons and then I go for the 4d. And if I'm making something from osmium or platinum, I remove the 6s electrons and then I remove 5d if I need to. So let's think, for example, about the configuration of zinc 2+. Zinc is another one of those ions that only forms one charge. We don't usually use transition metal Roman numerals for zinc because it's always 2+. Well, if we think about what the electron configuration for zinc would be, it would be argon 4s2 3d10. Well, think about it. If I remove the electrons from the 4s valence shell first, if I remove both of those electrons, I get 4s2 3d10. And those filled 3d orbitals are lower energy. The 4s electrons are lost, and the 3d remains completely filled. And that's why zinc is only ever 2+, because once I remove those valence shell electrons, it's now disturbing low energy filled orbital sets. So now what I want to do is I want to look at iron 2+ and 3+. And once we do that, then I want to look at para and diamagnetism, which is in the video demonstration on Google Classroom. So if I do iron +2 and iron +3, well, the first thing I had to think about is just what is the configuration for iron. So try writing the configuration for iron, and then I want you to try making iron +2 and try making iron +3, and then come back and check your work with the video. So iron has the configuration of argon 4s2 3d6. So if I lose 2 electrons, those electrons are most likely to be from the 4s, which would leave me with argon 4s0 3d6. Do you have to write the 4s0? No, not necessarily. I'm just writing it to emphasize where those electrons came from. Because I hate to tell you this, but it shows up on the AP exam enough times that I'm making a big deal out of it because I really want you to get these easy points that are just putting a rule in your head, because those are simple, and simple points are worth just as much as hard points. So if I make iron 3+, which is actually the preferred oxidation state for iron, then I'm going to have 4s0 3d5. That's the reason it is the preferred oxidation state, because it leaves me with the low energy 5 half-filled 3d orbitals. So now that we're thinking about removing these valence electrons from these transition metals, this would be a good time to think about paramagnetism and diamagnetism, which is in the YouTube video from the demo. So head over there, take some good notes, make some good predictions, and have a great afternoon.